Hello, hello. Good evening, everybody. I'm Dr. Amrita Bhattacharya, Assistant Professor in the Department of Mathematics, Kidderpore College, Kolkata. On the behalf of Seminar Subcommittee and the Department of Mathematics, we have organized a special lecture on the topic Recent Advancement in Black Hole Physics. And we cordially invite all of you to join the lecture and experience the evening that would be memorable to all of you for a long time. First of all, I am really grateful to our principal sir, Dr. Obhijit Ganguly, for giving me the opportunity to organize this special lecture. And I am also very much thankful to the convener of seminar subcommittee, Professor Tonika Bhattacharya, without whose inspiration it was difficult for me to conduct. I am expressing my gratitude to the IQAC coordinator, Dr. Swati Pal, the Teacher Council Secretary, Dr. Chandrabali Dash, all the respected GB members, and all the faculties of different disciplines for showing their immense interest in this topic. Next, I would like to request our respected principal sir to say a few words. I would like to request our respected principal sir to say a few words. Sir, your voice is not audible. Please check your mic once again. It is not audible. Please use device mic, sir. Sir, please unmute yourself. Nothing is audible, sir. Sir, nothing is audible. So I think there is a technical problem in our principal sir's microphone. So then I would like to request our respected GB members, our senior teacher, Dr. Subroto Bagchi of the Department of Political Science, to say a few words. Principal sir, nothing is audible from your side. Subrata da, is it audible?
I can hear you.
Okay, okay. So next, I'm going to invite our respected GB member, one of our respected GB member, and our senior teacher, Dr. Subrata Bagchi of Department of Political Science, to say a few words.
Okay, thank you, Amrita. I was actually waiting for our principal to speak out, but
Yes, yes, I can.
I think there is some technical glitch. I think that is why principal has not been able to join.
Yes,
This is the problem. So suddenly I am on the platform. Um,
yes.
um, this seminar, this webinar actually, mm, this is completely alien to me. It's because I am from political science, but that doesn't mean that I know that's physical science. And the topic chosen by the Department of Mathematics and our renowned reputed speaker, Professor Kamal Kanta Nandi, that has been extremely, I think, stimulating, as well as completely unknown to us. We have heard so much about the black hole theory, everything all right. But recent advancements in the black hole physics that is so out of our mind, but at the same time, it's what is out of our mind, what is unknown, that also has some attractions. And that for that reason, I believe that the audience will, today's audience will enjoy his lecture. And I feel so proud the Department of Mathematics has invited me to address this session. And I'm sure that our teachers, our students will learn many things from his lecture. A few little words about today's event is that black hole physics, as far as I know, few years back, I started to study the book of Stephen Hawking, The Brief History of Time. And I found that while searching one book from our college, in our college library, suddenly I found a book, The Brief History of Time. I started to study. I went through that book quite a number of pages, but after some time, I realized that the topic is not my cup of tea. Therefore, after some time, I left that book and didn't complete reading that book because the subject is difficult. I am not at all from any science background, but I believe that the topic is vastly interesting. Topic is so influential that it has changed the course of the cultivation of science in our country and all over the world. I think that that the people who are in the field of science, they find so interesting, so stimulating, and so challenging in studying this particular field of inquiry. I wish every success of this webinar, and I welcome I welcome and wish that Professor Kamalkanta Nandi's lecture today will will enchant our audience and will be charmed by his presentation. Thank you, thank you again. I congratulate Department of Mathematics for presenting this webinar today. And over to Amrita again.
Okay, thank you, sir. Thank you for sharing your valuable thoughts. Next, I would like to invite our IPSC coordinator, Dr. Shati Pal, to share her thoughts.
Good evening. Am I audible?
Yes, you're audible. You are.
Good evening. Thank you, Amrita. Good evening and welcome, Professor Kamal Kanti Nondi. Kidderpore College today organizes an international webinar on recent advancement on black hole physics. Now, origin of universe is a mystery to mankind. From philosophy to science, philosopher to scientist tried to get answer on this. Lot of research have been done in last 50 years on this issue. In 2017 and 2020, research on black hole was recognized by Nobel Committee by offering Nobel Prize. Today, Mathematics Department of Kidderpore College organized a webinar on this black hole theory. Though it is a much complex subject, but I am sure Professor Kamal Kanti Nondi will present in a lucid way, understandable by students and teachers of all branches. With this, I request Dr. Amrita Bhattacharya to introduce Professor Nandi and continue the session. Thank you. Over to Amrita.
Thank you, Shatiji. Thank you so much. Okay, now let me grab this opportunity to introduce our guest speaker to all of you. While at the first, I would like to express my gratitude towards him for sharing his valuable time with us. Our guest speaker is an eminent scientist and a promising personality in the field of astrophysics and cosmology, whose career involves professorship in applied mathematics in the University of North Bengal for 36 years, while at the same time being visiting associate at IUCA for 10 years and UNESCO visiting professor to Beijing from 1999 to 2008. Along with this long-term involvement in academia, he also served as an India CNR exchange scholar to Rome from 1982 to 1983, as well as India CNRS exchange scholar to Paris in 1988, and a visiting professor to Chinese Academy of Science in Beijing in 2004. Currently, he is serving as the professor and the director of Zeldovis International Center for Astrophysics, Ufa, Russia. He authored over 100 papers in peer-reviewed journals with more than 30 PhD degrees under his supervision. So, I am very happy to know that. So, please welcome Professor Kamalkanti Nondi to deliver his speech.
Mhm. Now I see myself.
Hmm.
Why don't I hear them? You are in the show, all right?
Professor
So
Nondi,
here,
you can start your speech. Is it audible? Am I audible, Professor Nondi?
have you seen Tulip before, Amrita? No. She is my sister's youngest sister's daughter. She is a professor in Kolkata college, in some college. As a daughter. So, okay.
Professor Nandi, you can deliver your speech
My
now.
son and she, they're just close together, and they were friends. They used to. Yes. Yes. Everyone can see and hear you, it says.
Yes, yes,
Is
you are
that true?
audible. You are audible. Professor Nandi, you are audible.
I think they had a problem, internet problem. It was- Should we start the picture share? I don't know. She has to. I thought she would. Oh. আচ্ছা ঠিক আছে
Okay, I think there was some kind of technical problems with our principal sir. I would like to invite him once again, Dr. Obhijit Ganguly, our respected principal sir. Please say some words. I'm requesting you, Dr. Obhijit Ganguly, our
No,
respected
I but
principal sir,
volume is
to
low
say
here, I
few
think,
words.
somewhere.
To
No,
say few
I kept
words.
the volume.
হ্যালো বড় মা
Okay. Hello? Hello?
Yes, sir, you are audible to us. Could you hear us, sir? Hello?
হ্যালো
Again, no sound.
হ্যালো I'm requesting our principal sir, respected principal sir, Dr. Obhijit Ganguly, to say a few words.
No? She asked me to use chord. This is the chord. But I hear nothing. At least I could hear something
Hello?
without the chord.
Principal sir is available now. He is showing that he is available now. I am requesting our respected principal sir, Dr. Abhijit Ganguly, to say a few words.
Ball. There is someone here. Okay. Hello.
Hello? Hello?
Hello.
Hello?
What is the date gone straight?
Hello? Hello? You are audible, Professor Nundi. You are audible. Can you hear me?
There is a date here. It doesn't appear.
It is appeared, but this.
I know, but how to make it? If you make it bigger, you don't see it either.
Try to.
No, it is blocked by this.
Yes.
Then okay, how to go? Click here. Doesn't go. Doesn't change to the other place. Other sheet. You showed that it was going actually nicely.
Yes. Yes.
Now it doesn't. To the next slide. Go to the next slide. Terrible. It was going very well.
Now.
I see. But where is the date? You do not see the full thing. You see? Somehow
Hello.
No, no.
What's my
Mhm. You are audible, Professor Nondis. Please say she can hear me. So, shall I start? Okay.
Yes, yes.
Shall I start? Yes,
Yes,
sir.
yes, yes.
Okay.
Yes.
All right. Uh, Good evening. Greetings from Russia and to Dr. Amrita Bhattacharya, Dr. Onitban Ganguly, and Dr. Swati Pal. My dear students and ladies and gentlemen, it's a great honor to be invited to give a talk on this topic, as you can see there. And do you hear me? I don't know. Okay. Uh, so, as you know that my friend is my colleague and my student is helping me, and he's here. Ramis is here. You must have heard of him. Okay. I'm a bit sad these days because of the war that's going on. You know, after all, Russia is my second home, and if my home is in war with another country, you feel a bit, worried, concerned. So therefore, I I have this concern. So with this concern in mind, I have to give my talk. So this is the title, Black Holes, and this is a hot topic today. And as you know that uh, as soon as man opened his eyes up to the sky, he saw many objects and wanted to know what they are, how they're moving. All these questions appeared in mind. So the investigation of these questions began in India. Thousands of years ago, we had Aryabhatta, Barahamihir, and they calculated the motion of planets around the sun and many other things. Ephemeris, for instance, in Bengali it is called Ponjika. And you can see there that everything like the eclipses, solar, lunar eclipses, tides, everything is accurately predicted. It's all, what is, she says that unmuted. It's unmuted. It is unmuted already. Do you hear me or not? Everything is fine, she says. And again, this message. All right. So, shall I continue? I do not understand this. Okay. So, it was 1,000 years before Galileo, Aryabhatta told and discovered that the planets are moving around the Earth, around the Sun, and he calculated the day and everything. And on the basis of this, we have ephemeris. So we can say when it will be eclipses, solar, lunar eclipse, and etc., etc., everything. This is remarkably accurate. When the sun will rise, when it will set. So as you can see, it was a very, very detailed calculation. It was, mind you, 1,000 years before Galileo. After this, all sorts of things happened: history, invasion, India, and the subjugation of foreign rulers. So, and people forgot all these things. But this knowledge somehow remained with us. We still have ephemeris in every house. Now, the formal investigation of physics began with Sir Isaac Newton. First of all, the three laws of motion, all of you have learned it in the school, three laws of motion. That if you do not disturb an object, it will continue to stay at rest or will go on with uniform speed forever. And number 2 is, of course, the P equal to mf. Everybody knows that. And the number 3, which everybody knows but do not understand, is the action and reaction. You see, of course, there is every action is equal and opposite reaction. And what is not often said in textbooks is that they act along the line joining the 2 points. Okay? And this action reaction law holds for gravitation only. It doesn't hold for instance, electromagnetic interaction, electromagnetic forces. They are at different directions. Okay? So Newton's law of gravitation. So 3 laws of motion, and then this law of gravitation, G m1 m2 by r square. I think the audience know it very well. And this is the famous story. Nobody knows whether it really happened that way or not, but people believe that this happened that way. All right. Of course, apples had been falling. Gravitation had been there even before Newton was born. So it has always been there. As soon as the universe was born, gravitation was there. So, all right. In any case, so this is a formal derivation, not derivation, it is intuition. It is just empirical fact that it works. And this works for the motion of apple, not only of the apple, but also for the motion of planets, as you can see. As you can see, big mass, small mass, and it moves in a Keplerian ellipse. The formula is Fgm1 m2 by r square. And so if you solve this formula, if you solve it, by the way, to solve it, you need calculus. And that was also discovered by Sir Isaac Newton. It was the great beginning of formal science. So this is the one. So this is m1 m2 by r square, mn by r square. And if you solve this formula, you get this ellipse. It is called Keplerian elliptic orbit. It is an ellipse. Okay. And for 200 years, it was discovered, it was found that this formula is right. And this was found by Kepler, that all the planets are moving around an ellipse, around the sun in an elliptical path. Johannes Kepler found it. And people believed, oh, okay, everything, gravitation was understood. And everything is elliptical, perfect. But there was a problem. After 200 years of all these things, it turned out that the planets do not move around the sun in an elliptical orbit. It moves like this. See? It is like a precessing ellipse. Not one ellipse, but many ellipses. Open orbit, it is open. Here it is closed, here the orbit is open, as you can see. This is the reality, this is wrong, this is right. Obviously, if this is right, then this formula doesn't hold. You see? That's why we need a new theory of gravitation. And it was not easy. So historically, people believe that maybe near the sun, there is a planet, tiny planet, living very near the sun, which is changing the motion of planets so that they become like this. They are not in closed path, but in an open path. And that planet was given a name, Vulcan. So with a lot of search, Vulcan was never found. Therefore, this theory is ruled out. It is a quite clean system. Only sun and the planets are there. There is nothing in between. So we are in the same problem as before. How to reconcile the force gmm by r square with the facts, namely the precessing ellipse. And there were many efforts, but it didn't work. And so we need to change everything. We need to change gravitational law. This doesn't work. Then people try to change the law. Maybe it is not gmm by r square, but r squared plus r to the power delta, something like this. It also didn't work. So therefore, new theory was needed. And this new theory is this. This is Einstein's. Oh, thank you. Thank you, Stravoni. This is Einstein's field equations. Now, it was after 200 years, 250 years after Newton that these new equations were needed, Einstein's field equations. Now, it looks simple, well, but these indices and all these things, those of you who are in mathematics or know differential geometry may find it okay, but others, well, this is a system of 10 independent, highly nonlinear partial differential equations, all symbolized into one line. Okay, it looks simple, but it is not simple. Okay, this is called Ricci scalar, Ricci tensor, this is Ricci scalar, this is metric tensor, this is matter tensor, this is gravitational constant, this is cosmological constant. Of course, you know cosmology, you heard the term. Cosmological, this is responsible for the expansion, acceleration of the universe, this gentleman. And of course, this is metric tensor like here. So this is the equation. It is a complicated equation. And to understand it, you need to have a little bit of knowledge of differential geometry, but everything can be done. Whatever man has done, other men can understand it. There is nothing magic in this. Okay, let's come to it. What is the meaning of this equation, grossly? So this is four-dimensional curved geometry. As you can see, Einstein said that there is no force. There is even no matter. If there is matter, it curves the space-time like this. You see, if you put a matter here, a ball, a solid ball, it will be like this. Now, this is matter. This is four-dimensional curved geometry. And if you go far away from this, it is flat. Okay, curved here, but flat here. I hope you understand this. Now, this was Einstein's idea. You do not see it. You do not see a network around you, but it is four-dimensional. And it is just a modeling of gravity, a modeling, four-dimensional modeling of gravity, four-dimensional curved geometry. Mind you, I do not want you to understand what is Ricci tensor, Ricci scalar, forget it. Just see what it is, like a story. So Einstein believed and he saw, he wrote these equations, and he said that if you have matter here, you curve the geometry like this. You do not see this geometry. It is there, a four-dimensional. It is not two-dimensional, it is four-dimensional. Here it is, you cannot draw four-dimension, but in two-dimension it is like this, and in four-dimension you can imagine it. It is not easy to imagine. In fact, it is impossible. Einstein could imagine it, we cannot. So this was his idea, that if on this side is matter, here, do they see that this cursor is moving? They don't see it. Okay, all right. So on the right-hand side is matter, cosmological constant, etc. And on the left-hand side is pure Riemannian geometry, curved geometry. Okay, so that was his idea. Nobody knew whether his idea would work or not. It was in 1915, but it was an idea. So matter, I want you to understand it very clearly. This is Einstein's equation. On the right-hand side is matter, material source, like we are, right? Wherever we are standing or sitting, all of you are sitting in the room, in your respective rooms, and around you, you have made this curve. You have made the space-time around you curved like this. You don't see it, but it is there. And not materially, but it's the modeling. If you ask me, is it really happening? I said, no, we don't answer this question. This is not a scientific question. What is really happening or not is what you observe. Does this model work? This is a scientific philosophy. You do any crazy model, like quantum mechanics. Okay? You do any crazy model, does it give you the results that you observe in the laboratory or in the sky? Okay? Then you can say, okay, this model, this formula, Einstein's field equations are correct. It turned out that these equations are correct. And we will tell this story and we will go all the way to the black holes. Mind you, don't lose track of where the story began. It began with the precessing ellipse, which required that the gravitation theory should be changed. And this is how Einstein changed it. That is matter on the one side and curved geometry on the other. So if there are M1 and M2, then you see there are two curved geometries. Okay, they are interacting with each other. Okay, let's for the moment take this. So I proceed further. I want you to understand it very clearly. If you want to read it again, you just ask me, I'll come back here. Okay, now here. Oh, so he is writing this equation. Life has become complicated after he wrote these equations. As many jokingly say, that when there was Newton, life was simple. You just had F equal to gmm by r square. But after he came to solve that precessing ellipse problem, life became complicated. But again, I want to tell you that, I forgot to tell you, that why Kepler didn't find this. Kepler found this and not this. Why? Why he didn't see it? You will be surprised to know that this big, it is very big. The shift of the angle, you see, the head is shifting. After one round, it goes here. Then after another round, it goes here. Then after another here, here, here. So there is an angle. So let us say this angle, this angle. So it is 43 seconds. If you wait 100 years on Earth, then the movement of this and the movement of this head is only 43 seconds. This angle. Do you know what is a 43 second? You have 1 hour, okay? You divide it by 3600. Then you have seconds, minutes, seconds. 1 minute is 60 seconds, and 1 hour is 60 minutes. So it is as small as that, okay? Divide 1 degree by 3600, okay? So little. And then you have to wait 100 years to see this shift, precision, okay, precision of the orbit. That's why at that time the telescope was not very precise. It was rather crude. So they thought that it was, Kepler thought that it is the same ellipse. He didn't see this shift, but it is shifting. This is the reality. And that's why we needed a new theory. This doesn't work. Newton doesn't work. But again, to say that Newton doesn't work is wrong. Newton works here, okay? Here in the flat, far away from the object. Here is Newton, and here is Einstein. Remember this, okay? That is, in the curved space, there is Einstein. Far away from it is Newton. Newton works. And if we didn't have Newton, Einstein's theory would be useless. Why it would be useless? It is because of the boundary condition, but I don't want to talk about it. Just know this. So this is the gentleman. As you can see, it is the Ricci tensor he is writing. Okay. Now, as we said that there is matter, matter means what happens to matter eventually? You see, this is the matter. This is nobody knows. It is a stellar nebula. Nobody knows what it is, how it all began. But we write it. Then it becomes a star. It's an average star. As you can see that here, the gravitation is always attracting, always attracting to the center. Always. It doesn't take a rest. If it takes a rest, then everything will go away from each other. And we shall even be going through the roof. Therefore, it becomes a star. It brings all the particles together, and it becomes a star like this. And what happens is there is a big friction, and then it ignites the fuel, hydrogen inside it. Hydrogen, it burns. So there is a huge hydrogen burning, which is going on in the sun. So what happens is if there is something burns, then there is a big radiation pressure. A big radiation pressure. Radiation pressure always works outside, it is anti-gravity. It works against the gravity. And gravity is always pulling inwards, and the radiation pressure is pushing outwards. So this push and pull together make a balance, and that's the boundary of the star. Okay, this is the average star. But then what happens is the fuel gradually diminishes, it goes away, and then becomes helium burning, because no burning can go on forever because the stock is limited. Therefore, it becomes a red giant. So here, the radiation pressure becomes more, and the gravitation becomes less. So it becomes a red giant. And then, when it becomes a red giant, it explodes. It explodes because, again, there is this friction frictional heat, and it explodes. When it explodes, it can become a white dwarf. So what happens? It explodes, and all the particles then again come back. Okay, because gravitation is there. Some go away forever, other come back and become a star called white dwarf. It was discovered by Subramanian Chandrasekhar and William Fowler. They were given the Nobel Prize in 1983. Okay, and this mass is 1.44 solar mass. Okay, this is the maximum mass of a white dwarf star. Now, what does it mean, white dwarf? Now, quantum mechanically, there is a story. Not story. I will tell you why. What is this? It has a density of 10 to the power 6 gram per centimeter cube. That means if you take a small piece of white dwarf star, it will be 10 to the power 6 gram, which means 1,000 kilogram. So you can imagine, you just take the piece of a Ludo, a Ludo piece, 1 cubic centimeter, let us say, and then it will weigh 1,000 grams. It is so dense, 1,000 grams. Now, how it has become like this? Because when it comes back here again, the electrons go into the proton, the electrons go out. These are all electron clouds. They go out. When the electrons go out of the nucleus, then it makes an electron gas. And the electron has a property. It is called degeneracy. It is Pauli exclusion principle, Pauli. It's a quantum mechanical effect. It means two electrons cannot stay in the same orbit. They don't like each other. Two electrons with spin half and spin minus half and plus half. Electron has spin. And they cannot stay in the same orbit, and they want to push each other out. Okay? So this is the pressure that keeps the white dwarf there. So there is a fight of electrons there, because electrons are in a free gas, and there are these protons. So this is how the white dwarf. So if protons come together, then the density is like 1,000 kilograms, like per centimeter cubed, which is like a Ludo piece. Okay, so you can understand. From here, this is the carrier of a star. Okay, is born, it's a small baby, then it is a young man, and then he dies, and then he becomes a white dwarf. This is one carrier. The other carrier it's a massive star. It is small here, but if the star is massive, again it becomes a red giant. It is called red giant. Okay, when the sun becomes a red giant, it will eat all of us. Okay, but don't worry, there are 5 billion years still there. We can live, and it will eat Mercury, it will eat Jupiter, it will eat Earth, it will eat up to Earth or up to Mars. It will eat all of them because it is a very big star. If sun becomes very big, then it will come near my window and it will eat all of us. Okay, don't worry about it now. So this is the red giant, and then it becomes a supernova. It's just a bursting. It becomes a supernova, and then it becomes a neutron star, or it becomes a black hole. Okay, and this neutron star is 10 to the power 14 grams per cent. That is the weight of a Ludo cube is 10 to the power 14, or so 10 to the power 11 kilogram. Can you imagine? Put 1 and 11 zeros, so many kilograms of a tiny little earring, like your earrings, tiny little. This is neutron star. What has happened is all the electrons have gone into the proton and become a neutron. So the whole star is a big neutron, very dense. It is a neutron star. All the particles are neutron stars. And they have all been observed by Hewish and everything. It's there. They are not stories. White dwarf has been seen, neutron star has been seen. But if the mass is above, called Oppenheimer-Volkoff limit, okay, you don't know it, but just know it. Just as here and here, if it is mass is bigger than the Oppenheimer-Volkoff limit, it becomes a black hole. Okay, so this is the story here. So this is the carrier of big star. This is the carrier of small star, and small stars become black holes, which is the topic of today. All right. This is Chandrasekhar and Fowler. They got this prize, and they discovered, predicted white dwarf stars, and it has been observed. The calculations, forget it. And if you come to study with me, I will teach you. Okay. Now, this is another. This is now, it has been observed, in fact, in the sky. If you see that, you see many pictures that there are a jet here and a jet there. You can see in the sky and two jets. I will also show you another jet there. Why the jets form? It is because everything in the universe is rotating. So you have a rotational energy. There are two energies. One is the thermonuclear fusion, which sustains our sun at this moment. But when this fusion is over, it is not much energy. But the rotational energy is much more. It is about 42% of the energy released. And this energy is going out this way and this way because this is rotating. This is the axis of rotation. And the energy is this way and that way. And this happens because the energy is interacting with the interstellar medium and this. But you cannot imagine how far they are from each other. 450,000 light years away from each other. Very large distance away. Okay, this is the black hole. Okay, and there is a galaxy around it. Okay, it is staying inside a black hole. Like the yellow of an egg. The egg white is here and this is the black hole. And these are the jets. And that happens because of the rotational energy is spent like this. Okay, this has been observed. Okay. Why did I? Okay, we come to here. By the way, before, if I don't come back here, this is called vacuum energy. Can it be made rotating? It doesn't. No, I did it. It could from here. Okay, forget it. By the way, this is vacuum, but not vacuum. This is called vacuum field. It moves. I don't know why it doesn't move now. All right. So, black hole. Just now we said that this is a black hole. Forget this. And this is the geometry. Let us remember Einstein again. So this is the black hole here. Now, we do not talk about material. We only talk about geometry because you cannot talk matter and geometry both because they're equal. So you have to choose. Which one would you talk? You have to talk about either matter or geometry. It's either or, not the two together because they're two different things. One is matter, the other is geometry. Okay, so we talk about geometry because this is Einstein's theory. We talk about geometry, we forget about matter. Now, this is black hole. This is the horizon. You see, if you follow this line and if you fall into this black hole, you cannot come out. Unfortunately, you cannot climb up the well. It is infinite well. You cannot climb up. And if you are somehow here around the rim, then it will take a lot of energy to get out. Okay? And if you fall in, then once you fall in, you will fall and fall and fall. You can never take your spaceship back. So this is black hole. This is one-way traffic. You can come in, but you cannot go out. Except, of course, Hawking radiation, that's another story. This quantum mechanical, but classically, you cannot go out. You can fall in only. So this is black hole, the geometry of the black hole. Exterior geometry, mind you, not interior. A black hole has interior and exterior. Every object has interior and exterior. So this is Hawking, you must have seen. And this is Roger Penrose, who got Nobel Prize last year. And these are the energy conditions of matter. I just mentioned it because you don't understand energy conditions and quantum evaporation of black holes. So, but I have to mention it just for you to understand the terms so that it is not unfamiliar to you. Even black holes die because of quantum evaporation, as was found by Professor Stephen Hawking. And there is this Hawking-Penrose energy conditions. If these energy conditions are satisfied, you say the matter is normal matter, and it can collapse to a black hole when it is interior burning energy dissipates. Okay, remember this. This is the validity of these conditions. If the conditions are not satisfied, then it will not go into a black hole. So this is their discovery. It has been, of course, we know that we have black holes. There is another object, wormhole, you see. It has two ends. One is here, the other is here. Two black holes. One is here, the other is here. Two black holes together, joined together at the throat. The minimum radius is the throat. Now, and this is a very interesting object. You see, it is like a twin black hole, you would say. Now, this is called wormhole. Why wormhole? Because it's like a hole, worm, like worms. You know, they eat, and go up and up there on this side. It can start from up to down and down to up. Now, the question is, you can identify the two ends. You see, it is infinity. This goes to infinity everywhere on both sides. So you can identify them. Okay, just join them together. So times flow at different rates, here, up there, and down there. The time rates are different. Okay, the clocks move at a different rate. Clocks move at a different rate. I mean, clock readings are different. So people say that you can make it, it leads to a kind of a paradox that if you are here, up there, and you can come down there, and you have, since there is the clock rates are different, so you can come back to your past, kid your grandmother, and you will never be born. So it is paradoxical, okay? But you are here, but you could do it. That is, you go against the evolution of time. We know that time follows always forward, but here you can go backwards in time. It is paradoxical. It is also called time machine. You must have heard of it. Warp drive. All these crazy ideas are connected to this wormhole. Why do you discuss this wormhole at all? Because this is also a solution of Einstein's field equations. If so, those complicated field equations, they have these field equations have this solution. It is a solution of the field equations, so it is respectable. And people are working. Dr. Amrita Bhattacharya also has done some work on this. So, and our group here in Russia and everywhere. Okay. We see that it is very difficult to distinguish between a wormhole and a black hole observationally. Okay, this is one of our predictions. You cannot say by looking at an object far away whether it is a black hole or a wormhole. So this is a technical discussion. We'll come to it later. Now let's stay in the black holes. Okay, forget wormholes. Now suppose this is the sun. I told you that around the sun you will find there is no sun. It is actually a curved geometry. Mind you, no sun. As I told you, either you talk about sun or about the geometry. Einstein talked about geometry and we talk about geometry. No sun. Sun is Newtonian, but the geometry is Einsteinian. Okay. Now, light move around this. What are these? Why it bends? If you look at this, no, sorry. You see, light moves around these lines, around these geodesic lines, shortest distance lines. You can see it. Okay, shortest distance lines. So it is bent. Light bends because gravitation bends light. Remember. So as you can see, from Earth, from a star here, at a star, you do not see the star. Why? Because there is sun here in the middle. It blocks the star, and you do not see it from Earth. Okay, but during solar eclipse, the sun is black, and you see the star not here. You see it up there. You see the star actually. It was observed, which means light bent. If you look at the picture carefully, it is the apparent position. Star is here, but you see it there. Okay, because light has bent. If light didn't bend, you would never see it there. Maybe you wouldn't see it ever. Since it bends, you see the light. You see the apparent position of the star there. Not here, but there. This is a straight line. So this is what it is. It's so tiny. This angle is 1.75 seconds. It was observed in Brazil in 1952 during the solar eclipse that this is true. there is a beautiful story about it. Max Planck, you must have heard of him. Max Planck was the discoverer of quantum mechanics. He didn't believe in such things. He didn't believe in Einstein's theory, actually, but it was early years. So somebody asked him that his Einstein student was Strauss. He said, "Sir, did you hear that Planck died last night?" And Einstein was thinking, "Oh, I see, it is very sad. He was the finest man and a great friend, Planck, Max Planck. But he didn't understand physics." He said, "How could you say such a thing about such a great physicist, great man, the father of quantum mechanics?" He said that in Brazil, when this experiment was done, when in Brazil, when it is day, it is night here in Europe, in Germany. So Einstein said that Planck stayed up all night. He didn't sleep to hear whether my theory was right or wrong. If he really understood physics, he would have gone to bed the way I did. It was a new experiment, of course. It was just fun, joke. So this is the point. I hope you understand. Light bends when it passes by the sun. And that's why you do not see. Whatever you see in the sky is not their actual position. You see everything apparent position, because the light comes passing through different intermediary objects like sun or anything. Light never comes to us in a straight line. We always see, objects that you see are apparent objects, apparent positions, not the real positions. Okay, this is one. It is called gravitational lensing. Like in the lens, the light bends, and you know it. Galaxies also bend light. So this is a quasar. Light comes to you on Earth from this direction, from this direction. So you see two images, because one is due to this and the other is due to this. So from Earth, you can see a quasar at two positions. These are apparent positions, of course. So this is the galaxy. This is the Earth. It has also been observed. These are the beautiful things. Or even if there is a black hole, then you can also find its image here and there. And there is an image separation, there is a flux, and everything has been calculated. We do the calculations here. Okay. These are the effects around black holes. This is an interesting thing. You see, if there is a black hole, of course there is a black hole, it has been discovered actually a couple of years ago. So you find that the description of things will differ completely. So somebody is sitting near the black hole here and somebody is far away. Okay, so what you will see that light is coming here and here and here, and as soon as it comes near the black hole, this gentleman far away will see that light has stopped. It is not moving. Even light, it has stopped. But this gentleman who is near the black hole will see that it is going with the normal speed. Now, this is the question. No one is lying. They're telling the truth. The faraway observer will say, yes, light has stopped here. And this observer near the black hole will say, no, it has not stopped. So their statements, their descriptions do not agree. Nobody is lying. But this is happening. And why this is happening? Because the space-time, as I told you, it is curved. You see, the light doesn't travel along a straight line. It travels along, curved paths, the minimal distances. These are called, in English, geodesics. So this is what is happening around black holes. This is very interesting indeed. So, this is mass. Okay. So what if the Earth becomes a black hole? What will be its diameter? It will be just less than 1 centimeter. So it will be like, I don't know, like your, in the ring, finger ring, the diamond in the finger ring. So it will be as small as that. Earth will be as small as that. And for Sun, it will be 3 kilometers. The radius will be 3 kilometers. If you put all the matter into the matter of the Sun within 3 kilometers, it will be a black hole. If they put all matter of Earth within diamond ring, it will be a black hole. So this is from Einstein's theory. All black holes are spinning. You see, this is the spin, and it is just cut. A black hole is cut in the middle, okay, just like an apple. So this is called event horizon. This is called ergo region, and this is a singularity. Of course, you do not understand singularity, and this is event horizon. Event horizon means that from here nothing can go out, nothing. Everything can come in. Okay, you do not see anything here inside this because nothing can, no information can go out except by Hawking radiation. I don't want to talk about it. So, so this is a spinning black hole because everything is spinning. Sun is spinning, Earth is spinning, every astronomical, astrophysical object is spinning. So this is the picture. Okay, and for a black hole, spinning black hole, it will be like this. The geometry, mind you, I'm talking about geometry. This is the interior, you see? You see the interior, this. And this is like this. You see, it's beautiful flower. It is not flower. It is pure geometry. You see the lines? These are geodesic lines, shorter distance lines in a gravitational field. This is the center, which is a very dangerous place. If you go there, you are dead. But you can survive here for a few seconds. So because you will very fast move around these lines. If you cross this, you will very fast fall and go straight there. Okay. So these are just geometrical, curved geometry. You see how peculiarly curved it is. Okay. So only geometry, mind you. It is not matter. It is not a flower. It is just geometry, curved geometry. That's all. And the center is called singularity. And this is the thing. Okay. So remember, inside the black hole, it is something like this. Somebody asked Kip Thorne, who won Nobel Prize for gravitational waves in 2017. Somebody asked him, "Sir, what is inside a black hole? What happens to the matter?" Yes, it could be Onyke Bordonasa, black holes and transits to other universes. Yes, as I told you that if you build a wormhole with two black holes like a dumbbell, I showed you the picture wormholes, so you can go from one universe to the other. Yes. So somebody asked Professor Kip Thorne that what is there inside a black hole? After all, it is matter that collapses into a black hole. So what is the matter inside? What is it nuclear matter? It is neutron star? No. White dwarf? No. Neutron star? No. Then what is it? Then Thorne replied that there is no matter. There is only geometry. Because we agreed that we shall talk only about geometry and not about matter anymore. Once we have Einstein's equation on the left-hand side and the right-hand side, I wrote to you, you remember. One side is matter, the other side is geometry, and we have to talk only about geometry. There is no matter. Matter is represented by geometry. Remember this word after you go home. Remember, matter is represented by geometry. And how do you know what kind of geometry? It is given by Einstein's field equations. Okay? So, this is the interior. Only geometry, no matter. Of course, we are not happy with this answer, but we have to believe it because this is Einstein's law, Einstein's theory. This is the two black holes colliding, you know. One is this, another is this. It happened that 1.4 billion light years away, two black holes of 29 solar mass and 35 solar mass, they actually collided. And when it collides in the space-time, as I showed you the space-time, you remember this network, four-dimensional network. This is the space-time. And this collision creates vibration in the space-time. Like if you throw a stone in the pond, then it creates waves. Similarly, when the two particles, black holes, collide very strongly, very hard, then it creates ripples in the space-time, like the water in the pond, ripples. And these ripples spread everywhere, okay? And if the collision is very strong, then the waves are also very strong, and it comes here. You see, these are the waves. As you can see below, these are the waves. Tonika, what is the best evidence of the existence of black hole. No. I will just come to it now. I will come to it. One is this gravitational waves, and this is the pattern of the waves, and this is the real. It was in Livingstone and Hanford. Yes, Hanford and Livingstone, they have been observed these gravitational waves. It is the result of collision that happened many billions, 1.4 billion years, light years away, and it has come today. That is, and there are many stages: before collision, after collision, all these things. And this is after collision. This is before collision. So this is what. Now, if you do a theory, it is called quasi-normal modes, and all sorts of theories are there. If you do a theory, then you will see that such waves imply that two black holes collided into one black hole, okay? And the energy released in the form of energy, which you see here as a wave. So these gravitational waves is a signature of the existence of black holes. Okay, this was the answer to your question. But there is another evidence. This is one evidence that these patterns will match only if you assume that the two black holes collided. Okay, black holes means horizon. Horizon, I told you that you cannot see anything beyond it. You can go inside the horizon, but you cannot get out of it. That's why it is called horizon. We often say that, oh, this man has a so small, limited horizon. Means he doesn't see beyond that. So it is like that, you know. So horizon is in that sense. You do not see the events below it. Above it, you can. But there are some ifs and buts, but that's unimportant. The important thing is horizon is a limitation of our vision, of our information. Okay? So therefore, these patterns will match only if the collision took place between two black holes, forming into one black hole with one horizon. So this is one thing. You can trust me because this is a bit complicated, but you can trust me. Oh, so these are the three people. What is Barry Barish, Kip Thorne, and Rainer Weiss. So they discovered the gravitational wave in America. Okay, great people. And he is also, he formalized one person. In a sense, our guru. Okay. Okay. I told you that these are the jets that you find. This is a black hole here. And if there is a normal star around a black hole, then this black hole, it is always hungry. It just eats the matter from it and makes it is called accretion disk. Okay. We do a lot of work in our laboratory on accretion disk. So you can say by studying the accretion disk, what is it there? Whether it is a black hole or a wormhole or anything. So this is a black hole around which you find a disk. It is called accretion disk. And this matter is supplied by the star here. The star actually goes into it here. It just eats the star. Okay. And when it eats the star, it just, the rotational energy is transformed into a jet like this. So this is the rotation axis. So the energy is going out through this, along this axis. So you see these things. In everywhere you will see this picture. These are called jets. This is the black hole, this is the accretion disk, and this is a normal star. So this is a picture of the black hole you will see. There is another picture. It is this. This is really a shadow. It is like a picture of a black hole. You can ask, did you see? How do you know picture? Instead of so gravitational waves was an independent confirmation. What can I say? Indirect confirmation of black holes. Okay, you see the waves and you do the calculations and you see it must be a black hole. This is a direct evidence. Tonuka, yes, did you ask the question? Okay, this is a direct evidence. You see, this is the black hole here inside in the middle. You see a black round. This is the black hole. And around it is bright light. Now you can ask, if nothing comes out of the black hole, as I say, that even light cannot come out, then how can we take it as picture? We take a picture when the light comes out. we take, you see, we cannot, of course, nothing can come out of here, but sideways, light can come from behind, mind you. Light is coming from behind, sideways, and this is this halo, sideways light, okay? But inside, you cannot see it, it is black. This is the picture of a black hole, okay? And it was observed by Andrea Ghez, who was given Nobel Prize. Thomas, in which medium the black hole collide? It is vacuum. How the amplitude is increasing with time. As you can see that I showed you, the amplitude is increasing with time. This is how the wave patterns are, because as it travels a long distance, okay, so these things are happening. There are detailed theories about it, but it happens in vacuum, because gravitational waves is like light waves which can travel in vacuum, no problem. Not sound waves. So, okay, so this is the picture of a black hole, and this was found by Andrea Ghez and others. So, very recently, maybe 2 years ago. Now, how do you know that you are really taking a picture of a black hole here? It could be something else. Maybe it is vacuum or nothing. Here is the confirmation. You see, this is the black hole here. It is in the center of our galaxy, and it is called Sagittarius S star. It is a name. It is a supermassive black hole, huge, 10 to the power 6 times the mass of the sun. Okay, every galaxy is having a black hole at the center, and here is our galaxy, our black hole. It is called Sagittarius S star. It is as big as that, and you see the orbits of stars around it. You see, these are the highly eccentric orbits. You see, highly eccentric. It's not like our solar system. Erratic, and these have been plotted by Andrea Ghez and co-workers. This shows that the matter here must be mass must be very high, okay? And a high mass located inside a very small area means it must be a black hole, okay? And it is a black hole. That's how we conclude about black holes. High mass, huge mass, localized in a small area means it's a black hole. Because of this eccentricity, high eccentricity of these orbits. These are stars, S1, S13, S12, etc. There are many stars. So remember this. This was one of the discoveries of Andrea Ghez. This is Andrea Ghez. Who is this man? Reinhard Genzel. And this is Reinhard Genzel. This is Roger Penrose, you saw him. The British man. He is German. She is American. So this is what they have discovered about the black hole at the center of our galaxy. This is their discovery. And it is understood that there are questions from Dr. Swati Pal. Why orbits are? Because it is very high mass, you see. Mass is very strong, huge mass. Huge mass means if something goes, then it will be eccentric. That's the idea. Question from Dr. Is there any relation with origin of life with black hole? That's a good question. I have no answer. I don't know. Really, I cannot answer this question. I would say the black hole is the result of collapse, where all life actually dies. Okay. Now, I really don't know if it is connected with the life forms. Okay, who is on naked bottom? Black hole absorbs matter. Yes. If the prior statement is true, then the universe is contracting due to existence of black holes. I can see it. Ramesh, I can see it here. It is blocked. Then why more? Okay. I understand your question, though I cannot read the entire line because it is somehow blocked by the pen computer. Okay. Now, your question. Hello. Your question is that if black hole absorbs everything, then why the universe is expanding? We must understand what do you mean by universe when you say universe. You know that a universe means even the galaxies, big galaxies, are just a dot. You think about a glass of water. All the particles are galaxies. All the water molecules are like galaxies. Okay? And they're far apart. I'm just giving you an example. They're incredibly, maybe 10 to the power 8 light years away, right? So they're far apart. And galaxies are points. So what is expanding is that galaxies are moving away from each other. Since we're talking about universe, I didn't. So they're moving away from each other, galaxies, okay? So, and actually they're accelerating. This have been observed by due to dark energy. Maybe in another time I'll talk about it. Now, what is a galaxy? How many stars are there? 10 to the power 11 number of stars. Please remember, on the average, each galaxy that you see as a dot. Remember, the universe is a fluid with all the dots of galaxies, okay? With all the fluid elements, the molecules are like galaxies. So you just imagine the scale of the size of the universe. Now, each galaxy has 10 to the power 11 stars, and stars much bigger than our sun. So, and the black hole, of course, is there in the center of the galaxy. It does absorb matter, which falls into it, true. But remember, it's in the center of one galaxy, which is just a dot in the universe. The galaxy, two galaxies as a whole, move away from each other. Okay? This has nothing to do with what is happening at the center of each galaxy. All right? Universe is far, far bigger than this. Okay? Where a galaxy is, even a galaxy is a dot. Just like, what can I say? Can you think about a dot? Just a small dot of a pen. Where is the black hole? Here. Can you tell me? So, of course, these things are happening, no doubt. The black holes can absorb material from outside. Mind you, there is one thing I would like to tell you. Remember this. What if the sun becomes a black hole tomorrow? Shall we be sucked into it? No. We shall barely notice anything. We will be moving around the sun, now a black hole, as before. There will be no change. You see, it is wrong to believe that if it becomes a black hole, we will all be sucked in there. No, the mass is the same. Only we shall not get light, heat, etc. That's a different issue. But the orbits of planets around the sun will remain the same. Okay? Again, red giant stage and all these things, remember, whether orbits will have a meaning when they will be eaten up when the sun was at the red giant stage. But assuming that we know it, so remember this. When you say black hole will suck everything, it is wrong. It will exert the same gravitational pull as it was doing before being a black hole. Remember, because the pull depends on the mass, and the mass remains the same. Okay? So, what is it? Here, this is the story. These are the people. Okay, thank you very much. If you have other questions, I will be happy to answer. Why orbits are eccentric? This I answered. Is there any relation about life? I don't know. And eccentric, I said it's huge mass. I answered.
Yes.
Yeah. If there is any other question. Oniket. Oh, thank you, Oniket. So this is the story as of now, of course. Yeah. Amrita. Dr. Bhattacharya. Yes, they're doing something. Hello, Amrita. What is it?
No person.
I see, I see.
Hello. Hello. Thank you once again, Professor Kamal Kanti Nondi, for delivering such a valuable speech and managed time from your busy schedule. You have explained the subject in such a easy manner that I hope all of them have
Hello,
enjoyed it a lot, in spite of they are from different backgrounds.
Amrita, would you like to say hello to Ramesh?
Yes, yes, yes. Hello.
Yeah.
Hello, Rami. It's very nice to talking with you.
This is Ramesh. Hello.
Okay, thank you. Okay, it's very nice to talk with you.
Aparna Pal. What is the time duration of a black hole? Ah, will it stay forever in the universe? No, that is a good question. Very good question. What will be the fate of a black hole? If Hawking evaporation takes place, that is, if it evaporates, if it emits Hawking radiation, then eventually uh, all of its energy will go out and leaving just a flat space, a vacuum. So this is a hypothetical thing that will be the end of the universe when all the black holes will eventually evaporate. Okay, evaporate, and that is nothing will remain. So, yes, if Hawking radiation is right, this we still cannot say with certainty if the evaporation takes place, but quantum mechanically it should.
Okay, thank you so much.
This
Is
is
there
really
any questions anymore?
question, really. Black holes will also disappear. It will not stay. So it will not stay forever. Yes, Apollo. We believe that it will not, because according to our Vedas, that anything that is created will be destroyed. So therefore, black holes will not stay. If it began from nothing, then it will end into nothing. And time scale, it could be any time. Just give any time. I see. Thank you very much. Oh, hello, Ramesh. Hello, hello.
Hello, hello.
See, show it, show
Okay,
yourself properly.
hello.
Do you see Ramesh?
Yes, 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 of course, I can see him.
Yes. Yes. Oniket. Oh, yes. Oh, it was very enjoyable meeting, and I am very happy. Upon. Oh, thank you, sir. We are grateful for it. Oh, thank you very much. I also enjoyed it. Indeed. Orthat. Thanks for wonderful. Itushi. Okay, thank you very much. Thank you, thank you. If I come to Kolkata, I shall meet you all once. Maybe we shall discuss about dark matter, dark energy, and all these things. Thank you so much, sir. That was so enlightening and enriching. Oh, thank you very much. I tried to do my best, but I believe that it could be better.
Thank you once again, Professor Kamal Kanti Nandi, for delivering such a valuable speech and managed time from your busy schedule. You have
Oh, she
explained the subject in such a
said
easy
she's
manner
very happy
that
to see
I
you.
hope all of them have enjoyed it a lot, in spite of they are from different backgrounds. Next, I would like to call Professor Tonika Bhattacharya from the convener of Cultural Subcommittee to share her vote of thanks.
Uh, Good evening, everyone. Am I audible? Am I audible, Amrita?
Yes, 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 you're audible. Yes.
Yes, of course. Okay, thank you. Good evening, everyone, to the one and all present here. the Honorable Speaker, Dr. Kamal Kanti Nondi, eminent scientist, professor and director of Zeldovish International Center for Astrophysics, Ufa, Russia, respected Principal Sir Dr. Abhijit Ganguly, IQAC Coordinator Dr. Shati Pal, Teacher Council Secretary Dr. Chandravali Das, and all the colleague friends and students attending the talk. I especially thank Dr. Amrita Bhattacharya, Head of the Department of Mathematics, for arranging such a scholarly and illuminating session on mathematical physics. It is such an honor to me to get the opportunity to thank you all. On behalf of the seminar subcommittee of Kidderpore College, I extend my gratitude to thank our honorable speaker, Dr. Nondi, to take out time from his busy schedule to speak on the groundbreaking discoveries on black hole physics, as well as in the field of astrophysics by 3 Nobel laureates, Roger Penrose, Reinhard Genzel, and Andrea Ghez. The extremely illuminating talk will definitely help us to contemplate the fascinating history of black hole science. I extend my gratitude to Aniket Bordhon, faculty of the Department of Journalism and Mass Communication, for technical support to make the webinar a success. Thank you all. With this, I end up my speech on behalf of the seminar subcommittee, Kidderpore College. Thank you very much. Over to Amrita Bhattacharya.
Thank you. Thank you so much. And I think the session is over now. So hope you will all enjoy it. And I'm really expressing my gratitude to all our viewers and audience for attending the lectures and for the valuable questions also. So sir is also very happy to attending your questions. So thank you so much. Thank you. Thank you. Good night.